Hi everyone and welcome to Smart Alex Coaching. In today's video, we're going to be looking at how to use Prim's algorithm to find the minimum spanning tree. In graph theory, a tree is a connected graph with no cycles, multiple edges or loops. On this slide, I've got examples of 8 graphs and we're going to go through all of them and identify which are trees and which are not trees. The first graph is a tree because all the vertices are connected. There are no cycles, multiple edges, or loops. The second graph is not a tree because we have these two graphs here being disconnected from each other. The third graph is also not a tree because we have a loop happening here. The fourth graph is a tree because we have got no cycles, multiple edges or loops, as well as all the vertices being connected to each other as well. The fifth graph isn't a tree because we have one vertex that is disconnected from the rest of the graph. The sixth graph is also not a tree because we have a cycle happening here. The seventh graph is a tree because all the vertices are connected. There are no cycles, multiple edges or loops. And the last graph is not a tree because we have multiple edges happening here. A spanning tree is a tree that includes all vertices of a graph. There is often more than one spanning tree associated with each graph. What I've got here are 3 identical graphs, and we're going to look at how we can generate different spanning trees from the same graph. In the first graph, I might like to include edge AB, AC, AD, DF, and FE. This is one example of a spanning tree we can create from this graph. In the second graph this time, I might like to include edge BC, edge CE, edge AE, edge DF, and edge EF. So this is another example of a spanning tree we can create. In the third graph, we might like to include edge AD, edge AC, edge BC, edge CF, and edge EF. And yet again, this is another example of a spanning tree we can generate from the same graph. The length of the tree is the sum of all the weights of the edges comprising the tree. A minimum spanning tree is a spanning tree for a given graph with minimum length. One way to find the minimum spanning tree is by using Prim's algorithm. The main idea of Prim's algorithm is that we want to create a tree by adding on the lowest weighted edge to the existing tree in each step. The methods are, first, you start off with any vertex. And in this example, I'm going to choose to start off at vertex A. I'm going to highlight it in green to indicate that this will be part of my final spanning tree. After we choose vertex A, we're going to identify all the edges connected to vertex A. There's AB, AC, AD, and AE. We then compare all the weights, 3, 5, 7, and 12. 3 is the minimum weight, which means we're going to include edge AB into our tree. Our tree now has 1 edge and 2 vertices, and we repeat this process. Remember, our goal is to include new vertices into our tree each time. So from vertices A and B, we can reach D, we can also reach E, we can also reach C via edge AC or via edge BC. We compare all the weights, 1, 5, 7, and 12. 1 is the minimum, which means that we're going to include edge BC next into our tree. Our tree now has 2 edges and 3 vertices. Again, we repeat the process. We still need to find ways to include vertices D, E, and F. So from our current tree, we can access D, E, and F as follows. via edge AD, AE, CE, or CF. Now note here that we don't have to consider edge AC, since both vertices A and C had already been included into our tree. We compare the weights of the highlighted yellow edges, 12, 7, 8, and 4. 4 is the minimum, so the next edge that we want to include into our tree is going to be edge CE. And this is what our tree currently looks like. We have to include 2 more vertices into the tree, which are vertices D and F. I can get to D via A. I can get to F via C, edge CF, or from D, edge EF. Note here again that we don't have to consider edge AC nor edge AE, since these vertices have already been included into our tree. We compare the weights 12, 8, and 3. 3 is the minimum, which means that EF will be the next edge to be included into our tree. This is what our tree now looks like. And we have one more vertex, vertex D, to be included into our tree. To get to vertex D, we can come from A, edge AD, or come from F, edge FD. When we compare the weights 12 and 4, 4 is the minimum, which means that we're going to choose to include edge FD into our tree. And this is the picture of our final spanning tree for this graph. In order to find the length of this spanning tree, we simply add the weights together, which are 3, 1, 4, 3, and 4. So the length of the tree is going to be given by 3 plus 1 plus 4 plus 3 plus 4, which is going to give us 15 units. Here's another example on how to use Prim's algorithm for finding the minimum spanning tree. Starting off with any vertex, in this example, I'm going to start off at vertex C. I'm going to highlight that in green to indicate that this will be part of our final spanning tree. We then identify all the edges connected to C. There are CA, CD, CE, and CF. We compare the weights 5, 9, 4, and 2. 2 is the minimum, which means we'll next include edge CD into our tree. Our tree now has 1 edge and 2 vertices. And we're going to repeat the process, identifying all the other edges connected to vertices C and D. There are CA, CE, CF, as well as DE. We compare the weights again, 5, 9, 4, and 3. 3 is the minimum. So next we're going to include edge DE into our tree. Okay, we repeat the process again. From vertices C, D, and E, it connects to CA, CF, and EF. Note that we don't have to consider edge CE since both vertices C and E have already been included into our tree. Comparing the weights 5, 9, and 5, 5 is the minimum, but it occurs in both edges. So it doesn't matter which edge you choose. I'm going to choose edge AC. And this is what our tree now looks like. We've got 3 more vertices to collect into our spanning tree. So repeating the process, from A, we can access B. We can also access F. From C, we can also access F as well. And from E, we can also access F as well. Comparing the weights again, 6, 10, 9, and 5. 5 is the minimum, so we're going to choose to include edge EF next into our tree. This is what our tree now looks like. 2 more vertices to include into our tree. To get to B, I can come from A via AB. We can also get to B via FB. We can get to G via FG. Again, we don't have to consider any of these vertices, AF, CF, nor CE, since these vertices have already been included into our tree. Comparing the weights, 6, 12, and 8. 6 is the minimum, so we're going to add edge AB next into our tree. We now have one more vertex to include into our tree, that is vertex G. To get to G, we can only come from B or F. When we compare the weights, 4 and 8, 4 is the minimum, so we're going to now include edge BG into our tree. And this is what it looks like, the final picture of our spanning tree. To obtain the length, all we do is we simply add the weights. 4, 6, 5, 2, 3, and 5. So the length is equal to 4 plus 6 plus 5 plus 2 plus 3 plus 5, which is going to give us 25 units. Thank you so much everyone for watching today's video. I hope you did like it and that you did learn something from it. If you did like it, please help us by clicking like below. If you have any suggestions on how we can improve, we'd very much welcome your feedbacks and comments below as well. We upload videos weekly covering topics from Year 3 to Year 12 mathematics. Our next topic will be Kruskal's algorithm, so make sure to subscribe. We'll see you next time. Thank you. Bye for now.